My name is Gomez-Rey, and this is my Physics 2211 lab report on the motion of a falling object. So in this lab, we'll be observing the motion of a falling object. In my case, we will be using a dry erase eraser, and we'll be observing it over Newton's second law, which basically states force is equal to mass times acceleration. Because we'll see that as the object falls, it stays at a constant acceleration throughout because of the mass. Um, we'll see an object falling from rest with a position versus time graph. We'll see a calculated um, model with graph and without graph. The experimental has drag force, but it's not calculated for. And then the model is calculated with and without the force to see the difference and how a drag force can actually play a crucial role. So the four main physics principles that we will be observing in this experiment is Newton's second law, which is F net is equal to mass times acceleration, the velocity update formula, which is final velocity is equal to initial velocity plus acceleration times time, change in time, the position update formula, which is position is equal to initial position plus v average times delta t, and F drag, which F would be being the drag constant and the magnitude of the velocity squared. So to start off with, we used a tracker model, and we're going to show the video of the experiment. We see the dry eraser fall, and we used the tracker to actually track the position, and we see that the position changes over time um, at a constant rate, which will make the actual acceleration constant. And we see that the average velocity was 0, negative 1, 0 in the y direction. So some observations were that in the tracker, the y-axis where the object begins falling. So as the value of y it decreases, the time increases, which was seen in the graph. And the line is exponential as it is moving at a constant acceleration, which we can be seen in Newton's second law. Some errors that might include in this experiment is that we didn't actually take the drag force into consideration, which in this case would be the air resistance, which could change the actual, which could change it because there was drag force, but we didn't take that into consideration, we would probably have different numbers. So here we see the glow script model without the drag. So our B is equal to 0, which means that there's no drag force and we're only taking gravity as the force into consideration. And we see here we put the initial velocity, the average velocity is negative 1. And then here we see the actual position versus time and velocity versus time graphs. We see that the velocity versus time is constant, and the position over time slowly exponentially accelerates, which shows a constant velocity, constant acceleration. So here's our gross code with the drag. So you can calculate drag since the drag force plus the force of gravity is going to equal to 0. So you can calculate this by plugging in the force of the gravity, which is mass times the constant of gravity, to find for B. And then here we see that we found it in line 70, and then we found the weight and added that together to find our F net. Here we see that our go script with the drag increases a little bit more exponentially, and there's more of a curve to it, with our B being 0.0034. So here, once we actually compare and contrast the experiment versus the model, we see that the model with drag is actually a lot closer to the observed because the observed actually did have drag, and the model without drag and just gravity falls at a faster rate. So with both things keeping in mind, both are consistent with the fundamentals physics principles. As seen in the graph, you can see that they follow similar patterns and trends as seen in Newton's second law, and in contrast, we have a drag force. Acceleration is reduced due to the resistance of the other force. So in conclusion, which models predict terminal velocity? It would be the same for both because the only force acting on it is gravity. So once gravity is the only force acting on an object, after some time it will equal to the magnitude of the drag force. Therefore, the net force will be 0, which will make the terminal velocity the same. What does this mean? The graph without the force is constant because the others only have one force. The graph with the drag force only has a slight curve because the velocity increases, drag force also increases, which leads to a decrease in net acceleration because they are proportional. And if would the terminal velocity be the same if the object was initially downward thrown? It would actually be the same because the terminal velocity is predicted from the drag force, and the weight of the force will be at some point equal to the drag force, which is then when the velocity will be constant based on Newton's first law. Thank you so much.